Imagine the universe is a giant video game, but with one twist: it has glitches. Physicists have identified at least 10 of these glitches in reality itself. They're not small errors. They're fundamental flaws in the fabric of space and time. From particles appearing from nowhere to the past rewriting itself, these mysteries show that our understanding of reality is incomplete. These aren't just puzzles, they're cracks in the code of the cosmos, waiting to be solved. So what are these glitches, and what do they reveal about our universe? Let's find out. Number 1, the cosmic dipole anomaly. The universe, on its largest scales, is supposed to be isotropic, the same in every direction. That's the cosmological principle, a bedrock assumption of modern cosmology. But recent sky surveys have revealed a persistent inconsistency. When astronomers count galaxies in opposite halves of the sky, they find a distinct imbalance, about 1% more galaxies in one direction than the other. This is the cosmic dipole. Some of this dipole is caused by our own motion through the universe, which compresses light ahead of us and increases the apparent number of galaxies there. Our solar system moves at about 370 kilometers per second relative to the cosmic microwave background, producing a well-measured temperature dipole in the CMB. 14%. However, after removing the motion component from the galaxy data, a strong dipole remains. 35%, 2 to 3 times larger than the motion can account for. This is not just a hint. It's statistically significant beyond the 5 sigma level, meaning there is less than a 1 in a million chance it's a random fluke. This level of confidence is the gold standard for a discovery in physics, ensuring the anomaly is almost certainly real. The finding has been confirmed in multiple independent surveys, including the WISE satellite and the 2-mass catalog, ruling out many instrumental errors. If the dipole is real, the standard model of cosmology is in trouble. The universe would have a preferred direction, a lopsidedness that defies the principle of isotropy. This assumption is so fundamental that without it, the equations describing the expansion of the universe would need to be rewritten. No one knows what causes it, perhaps a giant void, a remnant from inflation, or something even more exotic. This anomaly is a genuine glitch in the cosmic code, a crack in our understanding of reality that physicists are urgently trying to explain. Number 2, turbulence. The last great classical unsolved problem, turbulence, is the chaotic flow you see when smoke curls from a candle or water rushes from a tap. It causes bumpy plane rides and makes weather forecasts imperfect. It's happening inside your arteries right now. Turbulence is everywhere, yet it remains one of the most stubborn unsolved problems in physics. The core issue lies with the Navier-Stokes equations. These are the fundamental rules that describe how any fluid moves. They work perfectly for smooth, laminar flow, but when the flow becomes turbulent, they become incredibly hard to solve. In fact, mathematicians cannot prove that they always produce a smooth solution without contradictions. This is the Navier-Stokes existence and smoothness problem, one of 7 Millennium Prize problems. A correct proof earns $1 million, but no one has claimed it yet. What makes turbulence so difficult? It involves an energy cascade. Large swirling eddies break into smaller ones, which break into even smaller eddies, down to a microscopic scale where viscosity turns the motion into heat. This multiscale chaos happens simultaneously, making exact calculation impossible. We can simulate turbulence on supercomputers, and those simulations help design efficient aircraft and predict storms. But a simulation is not a theory. We still lack a complete mathematical description that starts from the basic equations and explains turbulence from first principles. So the next time you see a wisp of smoke, know that it represents a genuine gap in our understanding that has baffled scientists for centuries. Number 3, the black hole information paradox. Where does information go? Black holes are the ultimate cosmic trap. Anything that crosses the event horizon is gone forever, or so we thought. In 1974, Stephen Hawking proved that black holes are not entirely black. They emit a faint glow called Hawking radiation, caused by quantum effects near the horizon. This radiation carries away the black hole's mass, over unimaginably long timescales, until the black hole evaporates completely. Here is the problem. Quantum mechanics has a strict rule: information cannot be destroyed. If you burn a book, the information still exists in the ash and smoke, at least in theory, but black holes seem to break this rule. When a black hole forms from a collapsing star, it contains all the information about that star. When it radiates away, Hawking radiation appears random. carrying no trace of what fell in. If the black hole evaporates entirely, that information is lost forever. The equations say it is possible, but quantum mechanics says it is impossible. This contradiction is the black hole information paradox. It exposes a critical failure in our understanding. General relativity describes black holes as smooth, predictable objects. Quantum mechanics demands that information be preserved. The two theories cannot both be right. Physicists are now hunting for a resolution. One leading idea is the holographic principle, which suggests the information is actually stored on the black hole's surface, like a hologram. Another is the firewall hypothesis, proposing that the event horizon is a wall of energy that destroys anything entering, possibly releasing the information there. Both ideas push the boundaries of known physics. The pain of this paradox may be exactly what we need to forge a deeper theory of reality. Number 4. Dark matter. The invisible scaffolding of the universe. Galaxies spin so fast they should tear themselves apart. The visible stars and gas do not provide enough gravity to hold them together. Astronomer Vera Rubin was the first to prove this in the 1970s. She measured the rotation speeds of galaxies and found the outer stars were moving just as fast as the inner ones. By all known laws of physics, they should have been flung into space. Something invisible must be supplying the missing gravity. We call it dark matter. Dark matter is not a minor detail. It makes up 27% of the universe's total energy density. Ordinary matter, everything you can see, touch, or feel, accounts for less than 5%. We can map dark matter's presence through gravitational lensing, watching how its gravity bends the light from distant galaxies. The scaffolding is clearly there, but the material itself is a ghost. So what is it? Candidates include weakly interacting massive particles called WIMPs and hypothetical lightweight particles called axions. Physicists have built enormous underground detectors, hoping a dark matter particle will occasionally bump into an atomic nucleus. For decades, they have seen nothing. No credible detection has ever been confirmed. The particle remains stubbornly invisible. Dark matter is a glitch that hints at a whole new layer of physics. Our current theory of particles cannot explain it. We know its gravity. We cannot find its substance. It is the most abundant form of matter in the cosmos, and we do not have a single sample to study. Number 5. Dark energy. The accelerating expansion mystery. In 1998, two teams of astronomers studied distant supernovae to measure the expansion rate of the universe. They expected to see gravity slowing the expansion, like a ball slowing down after being thrown. Instead, they found the expansion is speeding up, a result that won the 2011 Nobel Prize for the team leaders Saul Perlmutter, Brian Schmidt, and Adam Rees. Something is pushing the universe apart faster and faster. That unknown force is called dark energy. Dark energy is the opposite of dark matter. Dark matter pulls matter together, building galaxies. Dark energy pushes everything apart, accelerating expansion. It is neatly spread throughout space, unlike dark matter which clusters around galaxies. It accounts for 68% of the universe's total energy density, far more than dark matter and ordinary matter combined. The simplest explanation is the cosmological constant. It says that empty space contains a fixed amount of energy that never changes. Albert Einstein first proposed this idea, only to later abandon it. But when physicists try to calculate this constant from quantum theory, they get a value 10^120 times larger than observed. This catastrophic mismatch is called the cosmological constant problem. An alternative theory is quintessence, which suggests a dynamic field that changes over time. Neither has been proven, and both remain open questions. Dark energy is perhaps the most profound glitch in physics. It challenges our understanding of gravity, quantum mechanics, and the vacuum. It is the most dominant component of the cosmos, yet the least understood. Solving this mystery will require a revolution in physics as big as Einstein's theory of relativity. Number 4. Matter-antimatter asymmetry. Why are we here? The Big Bang should have created equal amounts of matter and antimatter. For every particle, the early universe produced an antiparticle with the opposite charge. When matter and antimatter meet, they annihilate completely, leaving only energy. If the amounts had been equal, nothing would remain but radiation. No atoms, no stars, no planets, no us. So why does matter dominate? We observe that the universe is made almost entirely of matter. This imbalance is called baryogenesis, and the standard model of particle physics cannot explain it. The model does allow for a tiny asymmetry through a process called CP violation, but the effect is far too small. It is like trying to fill a swimming pool with a teaspoon. Physicists are searching for new sources of CP violation beyond the standard model. The LHCb experiment at CERN precisely measures how particles containing bottom quarks behave, comparing matter and antimatter versions for tiny differences. Another experiment searches for neutrinoless double beta decay, which could reveal that the neutrino is its own antiparticle. Such a discovery might provide the missing mechanism. So far, no new source has been found. The matter-antimatter asymmetry remains one of the deepest puzzles in physics. It is the very reason we exist. Solving it would reveal the laws that govern the universe's first moments. Number 3, the Mpemba effect. Why hot water freezes faster. If you put hot water and cold water into a freezer, the hot water can freeze first. This observation dates back more than 2,000 years. Aristotle, Francis Bacon, and René Descartes all recorded it. In 1963, a Tanzanian student named Erasto Mpemba noticed the same effect while making ice cream. A physicist later confirmed his claim, and the phenomenon now bears his name. Multiple mechanisms have been proposed, but none alone accounts for all cases. Evaporation reduces the total mass of water, leaving less to freeze. Convection currents accelerate heat loss by moving hot water upward. Dissolved gases that lower the freezing point are driven off during heating. Each factor contributes, but the effect persists even when these variables are controlled. Some experiments fail to reproduce it, indicating that subtle conditions such as container surface or water purity play a decisive. Number 2, quantum gravity, the missing unification. Physics rests on two pillars: quantum mechanics for atoms and particles, and general relativity for gravity and the cosmos. Each works beautifully alone. But when you try to combine them, the equations churn out infinite nonsense. That breakdown happens at the Planck length, a trillionth of a nanometer. Gravity becomes as forceful as quantum effects there. General relativity says spacetime is smooth. Quantum mechanics says it is grainy. They refuse to merge. That is our glitch. Why does it matter? Black hole centers and the Big Bang squeeze extreme gravity and tiny sizes together. Our theories hit a wall. They cannot describe what happens inside a black hole or at the start of the universe. These are not abstract puzzles. They are real places that demand an answer. Without a theory of quantum gravity, we cannot understand the universe's earliest moments. Physicists have proposed candidates. String theory says particles are vibrating strings, requiring 10 dimensions, 6 of which are curled up. Loop quantum gravity treats space itself as discrete quanta, like pixels, and predicts a minimum volume. Other ideas include causal set theory and emergent gravity. All are mathematically consistent, but none has been experimentally confirmed. Experiments like the Planck satellite and LIGO are searching for signatures, and both theories make predictions for the cosmic microwave background. The search for quantum gravity is the biggest challenge in fundamental physics. It demands a unification of the two pillars. Until we find it, the glitch at the smallest scales keeps our picture of reality incomplete. Once solved, it will transform our understanding of space, time, and matter. Number 1, high-temperature superconductivity, the race for room temperature magic. Electricity meets resistance and loses energy as heat, but some materials, when cooled, become perfect conductors with zero resistance. This is superconductivity, and it could enable lossless power lines, floating trains, and powerful magnets. But until 1986, superconductivity only occurred at extreme cold, around -269 degrees Celsius. Then a ceramic made from copper and oxygen shattered that barrier, working at -238 degrees Celsius. A new family of high-temperature superconductors was born. The Standard Theory, BCS theory, explains low-temperature superconductivity. It says electrons form pairs by riding on vibrations of the crystal lattice. This mechanism sets a maximum critical temperature. The new materials, cuprates and iron-based compounds, operate far above that limit. The vibrations are too weak to create such strong pairing. So what holds the electron pairs together? Proposed candidates include magnetic fluctuations or electronic correlations, but a complete theory remains elusive. Without understanding the mechanism, researchers cannot design new superconductors rationally. They must synthesize and test thousands of candidates. The goal is to find or design a superconductor that works at room temperature, an achievement that would revolutionize technology, but that goal requires solving this glitch. It is one of the biggest ongoing mysteries in condensed matter physics. Number 2, the glass transition, amorphous solid silent mystery. Glasses look solid, but their atoms are jumbled like a liquid, not stacked in neat rows like a crystal. This strange state forms when a liquid cools so fast that the molecules do not have time to organize. They simply lock in place. The moment this happens is the glass transition, and it might be the most common solid you do not understand. In an ordinary freezing, molecules arrange into a crystal at a precise temperature. In a glass, the cooling liquid just gets thicker and thicker. Its viscosity climbs by a factor of 1 trillion or more. The relaxation time, how long molecules take to rearrange, becomes longer than human observation. That is why glass feels solid. But this slowing down is not exponential in the normal way. It follows a stretched exponential, meaning it deviates from simple predictions. No one fully knows why. The deeper puzzle is whether the glass transition is a true thermodynamic phase transition or just a kinetic arrest. Some theories predict an ideal glass transition hidden far below the accessible range, where the entropy of the liquid would finally match that of the crystal. But that state can never be reached because the material becomes too sluggish first. And there is no clear order parameter that jumps at the transition. The system is stuck out of equilibrium, and its properties depend on its thermal history. Despite decades of research, a complete theory of glassiness remains elusive. The glass transition is a reminder that even everyday materials can defy a clean physical explanation. The glass transition and every other glitch in this list share one common truth. Our understanding of physics is still full of massive holes waiting to be filled. These glitches challenge everything we think we know. Thank you for joining us on this journey through science's greatest unsolved puzzles. Which of these 10 glitches shocked you the most? Drop your answer in the comments. And if you enjoyed exploring these unsolved puzzles, make sure to subscribe for more deep dives into the unknown.